All right, well, welcome back again. We are continuing our series on overview of calculus. And so just as a reminder, this is Calculus 5th edition by James Stewart. I'm copying verbatim a lot of things from there. So right now we are going to talk about continuity. So continuity, a function f is continuous at a if the limit as x goes to a of f of x equals f of a. So this implies also not only this last statement, but it also does imply that f of a is defined so that a is in the domain of f. And it also does imply that the limit as x goes to a of f of x exists. So that's implicit in assuming that this f of a is there and that it's equal to this limit. So what this essentially says is relatively important. It says that the continuous functions have the property that if you make small changes in x, it should produce only a small change in the value of f of x. And so as you, in fact, if you make the difference between, so as you make these small changes smaller and smaller, then you will get smaller and smaller changes in f of a. And we can see how that is sort of implied by this limit here. So then you can also define continuity for the left and the right hand limits. So a function f is continuous from the right at a if the limit as x goes to a plus f of x equals f of a. And you could say a similar thing about continuous on the left, where it would be goes to a minus. So then also we can talk about continuity on an entire interval. So these have been continuity at points. Let's talk about continuity on an interval. So a function f is continuous on an interval if it is continuous at every number in the interval. And then you might say, well, what about if the interval is a closed interval? So it includes its boundaries. So then if f is defined only on one side of an endpoint of the interval, then continuous to the endpoint endpoint signifies continuous from the right or left, depending on which side the endpoint is on. That's the wrong spelling of continuous, sorry about that. So then you might say, okay, so which functions are continuous on intervals? So polynomials, root functions, square root, and other roots, root functions Rational functions, which we said was ratios of polynomials. Trig functions are continuous at every number in their domains. A few more things about continuity. Continuity is actually relatively important. We do use this in proofs, except usually not with single variable functions. But if you don't understand it with a single variable, it will be hard to understand it with multiple variables. So as you can see, continuity is defined with respect to what goes on with limits. Okay. And so then just some more random points, like 2 more random points. So if f is continuous at b, and the limit as x goes to a of g of x equals b, then the limit as x goes to a of f of g of x equals f of b. Or in other words, the limit as x goes to a of f of g of x equals f of the limit as x goes to a of g of x. So what you can see here, f is continuous at b. There's the caveat. If f is continuous at b, and the limit as x goes to a of g of x is b, then I'm able to sort of translate the limits through the function. So f is continuous at b, and this limit of the inner function, this is the composition of functions, so the limit of the inner function of this composition is a certain number that the outer function is continuous at, then you can kind of move the limit like that. And so the last one here is the intermediate value theorem. Which is useful for knowing why it's okay to do certain methods of searching for roots of a function. So suppose that f is continuous on the closed interval AB, and let n be any number between f of a and f of b, where f of a does not equal f of b, then there exists a number c in AB such that f of c is equal to n. So it says that if you have a function f and it's continuous on an interval, then if you have a number between f of a and f of b, where those are not equal, then there must be another number c between a and b, where f of c is equal to n. Okay, so now we're looking at chapter 3. So chapter 3 is where we actually start talking about differential calculus. So the ways in which things will change as other things change. So derivatives are actually a special type of limit. So I think that it's interesting to remember that this is actually the fundamental definition of a derivative. Derivative is actually a special type of limit. And so the derivative of a function, here's the definition. At a, denoted f prime of a, or in other ways that we are familiar with, is f prime of a equals the limit as h goes to 0 of f of a plus h minus f of a over h, if this limit exists. So note that because limits don't always exist, derivatives can also fail to exist if this limit does not exist. So a function may not necessarily be differentiable at every point. And so then you can also transform this. So you can transform this by saying, let me set x equals a plus h, and let me then rearrange this and say that this implies that h is equal to x minus a. So when I see h, if I put x minus a in both of these parts of the equation, what I get is that f prime of a is equal to the limit of f of x minus f of a over x minus a. The only other part here that we have to figure out is how to transform this h goes to 0 into something in terms of x. You can see here h is going to go to 0 if x is approaching a. So this would say x goes to a. So then that's our definitions of limits, or sorry, of derivatives. I think that that's really helpful because the formal way to get a derivative then is by taking limits. So I know that in class, a lot of times we'll learn all these, or in maybe your prior calculus, you learn a lot of sort of rules, but I think it's really important when to keep in mind, what are we really working with? We're not just working with rules. Those rules are derived from the fundamental definitions of limits for derivatives. And so let's, for example, look at how you would get f prime of a if your f of x was equal to x squared minus 8x plus 9. So then in this case, you would get f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a over h, if you look at those definitions of the derivative, which this then, we start to plug in f of a plus h coming from this equation to f of a. So you would do the limit as h goes to 0 of, and then you would say, okay, a plus h squared minus 8 times a plus h plus 9 minus, and then here I'm going to plug in a for x. So minus a squared minus 8a plus 9 over h. And then if you keep reducing it, so you multiply out the squareds and you cancel lots of terms and things like this, eventually you'll get that this is the limit as h goes to 0 of 2ah plus h squared minus 8h over h. And then so remember that when we're taking limits, we don't actually care about what happens at the point we're taking a limit of. So if we cancel out here the values of h, since we're looking when h goes to 0, and then we don't care about the point where h is really 0, we can do that thing we did in the last lecture where we say, okay, I'm going to look at a function that is equivalent to the prior function at every point except the point where I'm getting the limit, which is at 0. So then this is going to be the limit of 2a plus h minus 8, which is equal to 2a minus 8. And look how interesting that is. That would also be what we would get if we use our typical derivative rules. So that's important. Now, I was mentioning in the lecture for the first chapter of our course textbook that when you think of something like dy over dx, this really is then not a ratio. So if people think of the separation of variables, I was mentioning how you like the things that we were doing with the differentials seemed a little wonky, and that would mean if you understand that, that means you really understand calculus. So this is not a ratio, right? This is an expression that actually means it actually means these limits. So it's not really a ratio. It's a notation for this limit definition of a derivative. And so that's why we did have to justify what we were doing in separation of variables, which we did in our separation of variables lecture. And so then finally, let's talk briefly, let's give a few more points. These are just a few more things from the textbook. So a function f is differentiable at a if f prime of a exists. Note that that means that you have to have a limit that exists. And then, so this is differentiability at a point, means that the limit definition of the derivative holds so that that limit that represents the derivative exists. So it is differentiable on an open interval AB, or on other types of open intervals if it is differentiable at every number in the interval. Note then also that I highlighted the word open here. So this is then removing the concern about what happens at the endpoints. So it's saying like, okay, well, we're not going to consider the endpoints. We're going to call this differentiable on an open interval if it's differentiable at every number in the interval. So I don't have to consider endpoints in this. So here's another important point. So if f is differentiable at a, then f is continuous at a. But this is not always true. So you can have functions that are continuous but not differentiable. So I think this is important to remember, because when we talk about our definition of what is a, what does it mean to solve a differential equation? And then we do say that you need to have a differentiable function. So you need to be able to take its derivative. So the solution is going to have to be differentiable, because or else how are you going to get a differential equation from the solution? You're not going to be able to take its derivative. But just because a function is continuous, so if you have a continuous function, that does not necessarily mean it's differentiable. So it's important to note that the differentiability here is stronger than continuity. So you can have continuous functions that are not differentiable, but every differentiable function is also continuous. Okay, that is today's installment of review of calculus as it pertains to review for advanced engineering mathematics.